All right, so we're starting chapter 14 now. This is section 14.1. Now, chapter 14 is a little bit different from what we're used to. It's a lot of higher level mathematics, so this is kind of bridging you into your next college algebra class. So there are two things in this section. This is about sequences of numbers, and there are two things to talk about. The first is we need to be able to write a sequence, in its general term, what I call form, and find terms of a sequence. And the second thing is to solve problems. That's not how you spell problems. With sequences. So, sequences at their heart are just lists of numbers. That's all they are. They're a sequence of numbers. And in this case, they're a sequence where order matters. Now, sometimes this order can be described using a nice equation, sometimes it can't. But the order of a sequence is important, and there are two classifications. The first is infinite sequences. And we know a couple famous infinite sequences, the integers, the real numbers, and so on. Etc. And the other main type of sequence are finite sequences. And these are finite sequences, finite list of numbers. Of course, contrasting with infinite sequences that are infinite lists of numbers. So, when we're talking about sequences, they are built from what we call the natural numbers. And we build them off of a domain. So the domain of a sequence is the set of natural numbers Now, the natural numbers are something we already know. They're just the positive integers. So 1, 2, 3, etc. Notice we don't include 0 here. Sometimes people include sequences with 0, but in general we do not. And finally, all sequences, whether it's infinite or finite, all sequences have the form a sub n equals f of n, where n is a natural number and f is a function. So one of the most important parts of a sequence is figuring out what this f of n is. And that's basically half of the battle that we encounter when working with sequences. So let's look at a couple examples. Starting with a sub n equals 2 to the n. And we're going to say this is the infinite sequence. So this is an infinite sequence because we can always take higher and higher powers of 2. So when you're talking about the terms of a sequence, the first term is always a1 or a sub 1. And in this case, this is 2 to the first. A sub 2 is 2 to the second. A sub 3 is 2 cubed, and so on. And this will continue forever and ever and ever. Now this, you may notice that because we're building this off of the n, 2 to the 1, a2 is 2 to the 2, a3 is 2 to the third, that pattern is not unique to this sequence. In fact, all sequences are built off of, if they can be, some pattern based on the first term. Now, sometimes that pattern, like I said, can be written into a nice equation, and sometimes the pattern can't be represented as an equation. Sometimes it's a more complicated thing, like, take double this and then add it to the third term that was before it, and so on. So for our purposes, we're going to be studying primarily sequences that can be defined by a general term like this, an a sub n. So you can think of a sequence. It is a list of numbers that follows a pattern. Sometimes that pattern can be in an equation form. Sometimes that pattern can be just a paragraph describing it. And one of the bigger things that we do in mathematics when we're dealing with sequences is trying to identify that pattern, because once you know the pattern, you can get any term you want. So a very common question that you'll see is let a sub n, so when you see the curly braces like this, that's your clue that this is a sequence. So this notation here, this represents the entire sequence. So this is all the numbers that satisfy whatever rule you're going to be given for a sub n. So let a sub n be a sequence defined by a sub n equals 1, 4, 9, 16, and so on. So now some of you might jump immediately and go, oh, I see the pattern, and that's great. But know that there are some requirements in math when we are proving something. It's a good idea to check at least 3 instances of that pattern occurring. 2 times is a coincidence, and the third thing could break. 3 times is much less likely that it's going to be false, and you can be just careful enough and check 4, especially with something like this and these types of problems. So a sub 1 is 1, a sub 2 is 4, a sub 3 is 9, and a sub 4 is 16. So what we're looking for is a link between these pairs of numbers that all follows the same pattern. So the connection between 1 and 1 has to be the same connection between 2 and 4, has to be the same connection between 3 and 9, has to be the same connection between 4 and 16. And that's got to be true of everything. So you may look at this and say, okay, well here n equals 1. Here we have 2n equals 4. Here we have 3n equals 9. And here we have 4n equals 16. And we know this because in this case n is 2, in this case n is 3, and in this case n is 4. And what we can notice is that all of these are n times n, n times n, n times n. Or, in other words, a sub n equals n squared. And this will allow us to find any single term. So, now that we have this, a sub n, we want to also look at what we would do if we were finding terms. So this is finding the general term. So for this problem, we're going to let a sub n be the sequence defined by the general term a sub n equals -1 to the n over 3n. And I would like you to find a sub 100, b, excuse me, the 15th term, c, a sub 8, and d, the 11th term. So I would please encourage you to pause the video and try this out. Try and find these 4 terms. I'm going to walk through the answers now. So in part A sub 100 equals -1 to the 100th power over 3 times 100. This is -1 to an even power is going to be 1 over 300. And that's our answer for A. Part B, the 15th term is a sub 15, which is -1 to the 15th power over 3 times 15. -1 to an odd power gives us -1. 3 times 15 is 45. So our 15th term is -1 over 45. A sub 8 is -1 to the 8th power over 3 times 8. Again, -1 to an even power is going to give us a +1. 3 times 8 is 24. So our answer here is 1 over 24. And then finally, the 11th term is a sub 11, which would be -1 to the 11th power over 3 times 11. -1 to an odd power keeps it -1. 3 times 11 is 33. So those are our 4 answers. So, last part of this section is just giving you some practice problems, finding general terms, identifying patterns. So if you like puzzles and you like patterns, you will most likely take 2 sequences a little bit better than some of the other things we've studied. So for this, given the sequences below, identify, not enough space for identify the general term a sub n. So I have 4 sequences: 1, 1/2, 1/3, 1/4, 1/5, etc. Then -3, -6, -9, -12, etc. And then -4, 16, -64, 256, etc. And 3/17, 3/34, 3/51, 3/68, etc. So I would please encourage you to pause the video, try and figure out what the pattern is for each of these. Now there's not a lot of work, it comes down to how you think about things. So trying to figure out the pattern for each of these is, so I'll start walking through it now. So each one of these, A1, A2, A3, A4, and A5, we're looking for, going all the way down, connections starting with A between 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5. So this one is pretty straightforward. It has to be 1/n. Or, if you want to be fancier, n to the -1. There's no other choice for it. For part B now, we're looking at connection between 1 and -3, 2 and -6, 3 and -9, 4 and -12. Well, all of these are exactly -3 times these values. So this a sub n must be -3 times n. For the next one, we have -4 is connected to 1, +16 is connected to 2, -64 is connected to 3, and +256 is connected to 4. So this one's a little bit more challenging. One thing, if you were paying attention to the last example we did, if we want this negative to switch between positive and negative, like this, we know that we're going to be raising some sort of -1 to a power. Now that power, when we raise -1 to an odd, it will stay negative. So 1, 3, and 5 should be negative, and it would be. 2 and 4 should be positive, which they are. So we know that this is just to the n. We'll take care of this. And so then we're really looking at what's the connection 4 to 16 to 64. Well, 4 times 4 is 16, 16 times 4 is 64, and 64 times 4 is 256. So all of these are just timesing the last one by 4, which is the same as raising 4 to the power of n. Now since both of these exponents are n, we could also write this as -4 to the power of n. And that would be our general rule. And then finally, in part D, we're trying to connect 1 to 3/17, 2 to 3/34, 3 to 3/51, and 5 to 3/68. Now, since all of these have 3 in the denominator, I know that my general term is going to be 3 over something. So really, I'm not worrying about 1 and 3. I'm worried about 1 and 17, 2 and 34, 3 and 51, 4 and 68. So, what is the relationship between these values? Well, 17 is 17 times 1, 34 is 17 times 2, and 51 is 17 times 3. 68 then, doing a quick check, is 17 times 4. So that means that this is nothing more than 17 times n. So there is a relationship that we're building here. When you look at the difference, especially in these last two, this was all times 4 times 4 times 4. But just looking at the denominators to here, to go from here to here, we did plus 17 and plus 17. And then from here to here as well is plus 17. So there is a difference to how things get set up. When you are multiplying by a common number, you're going to be raising to an exponent. When you're adding a common number, you're going to be multiplying that common number by n. So these two problems here are examples of what we call arithmetic and geometric series, or arithmetic and geometric sequences. And the next section, 14.2, is all about these two types of sequences. And there's some special things that we end up being able to do with them. But that is going to be the end of 14.1 for us.